All right. I'm employed by Siemens Healthineers. In traditional quantitative mapping, we use an analytical model to fit a signal model onto the series of images. And typically, these models are derived from the MR physics, for example, using the Bloch equations. However, the Bloch equations are fairly simple, and often we use assumptions to simplify them and have a well-conditioned fitting procedure. And a very prominent example is that we could, for example, assume that in a CPMG sequence that the refocusing pulse is ideal. However, in the real world, we have slice profile and we have B1 inhomogeneities. So this assumption is not really true, and we have effects which are called stimulated effects. Basically, we get a modulation on top of our mono-exponential decay, which is when we then fit a mono-exponential decay on top of this stimulated echoes, we result in an overestimation of T2. This becomes very obvious when you go to high field. For example, here you can see a data set from 7 Tesla. And if you use a standard exponential decay, you have an overestimation of T2, especially at the rim of the brain, which is due to the B1 inhomogeneity. What you can do is then you make your model more complex, which then also accounts for the stimulated echoes. This has been done using Bloch equations or, for example, an analytical solution for this effect. And then you get to a more accurate estimation. However, then you have more free variables. For example, you also have to estimate B1, or you measure it with a different sequence. And you still have assumptions. For example, you fix your T1. So in the end, it's very similar. We have, when you design a model for the quantitative imaging, you can end up with a very simple model, which is maybe biased due to this oversimplification. Or you end up with a very complicated model, which is then difficult to fit because your signal maybe not encode well enough this effect. Typically, these models are then validated using gold standard values, gold standard acquisitions. For example, for T2, using a single echo spin echo sequence, or for T1, using an inversion recovery sequence. Should be noted that we cannot use these gold standard methods within the clinical routine because they're just too time consuming. Here we want to exploit the idea that instead of deriving the signal model from the MR physics, we could maybe use machine learning to learn a model which associates the gold standard values to a certain decay that we could measure. To show you this proof of concept, we tried this on the T2 mapping using this CPMG sequence. So we acquired a host sequence, so this sequence we later want to use in a clinical routine, which is the CPMG sequence, and a gold standard method, which is in this case the single echo spin echo sequence. The resolution of both sequences were matched. However, we had 40 slices for the CPMG sequence, so we covered the entire brain, whereas for the gold standard method, we could only use 3 slices due to the time constraints. 3 subjects out of these 4 subjects we used to learn the model or train the model, and then we used the last subject to test this approach. So now we have a set of spin echo data and we have a set of CPMG data. And first we want to find out what are the gold standard values for this data set. So we perform this standard mono-exponential fit to get our gold standard T2 map. And then we are only interested in the actual brain tissue. So what we do, we apply a manually drawn brain mask. So you get a vector of gold standard T2 values. Now we can apply the exact same brain mask on our host sequence, so the CPMG data set. So you basically get a matrix with exactly the same samples as in the vector of the gold standard values, but also your decay, so you have your echoes in the rows of your matrix. And then we normalize this data to account for proton density effects. And now you have a very simple, typical machine learning problem where you have a set of decays in your matrix and you have a target value, your gold standard T2 value. So you can use shallow machine learning approaches to learn this association. And at the beginning, we started using a shallow neural network with an input layer of 6 neurons and fully connected 2 hidden layers with each 16 neurons. So it's a very shallow network compared to what we've seen. Also, we tried a very simple approach of just a simple linear regression, where X is basically the matrix of the case, and Y is your vector of gold standard values. However, if you look into the T2 values in a gold standard vector, you see there's only a very few high T2 values and a very few low T2 values, so the data is actually imbalanced. So in order to account for this, we used W matrix to weight the least squares fit. Then, after learning this sequence, you can use this regression model or this network to reconstruct quantitative T2 maps of the 4th subject, which was not used in the training data set. Here you can see the results. First, the gold standard method with the spin echo data on the very left, and then the 2 different data-driven approaches, either using the regression or the neural network. And for comparison, we also did the traditional mono-exponential fit, and you can already see that the T2 values for the mono-exponential fit are overestimated due to the stimulated echoes that I explained earlier. The data-driven approach is using a machine learning model, results in similar values than seen in the gold standard method. However, you can see that the regression seems to be a bit more sensitive to noise since it results in more noisy T2 maps. We also did a region of interest analysis where we looked into the T2 values of certain structures in the brain. And again, if you look into the exponential fit here in orange, you can see that the values are overestimated compared to the gold standard values, which is not surprising due to the stimulated echoes. Whereas the data-driven approaches seem to result in similar values as the gold standard method. I just want to point out the globus pallidus, where the networks seem to still overestimate the T2 values. And my assumption is it's because of the unbalanced data, which we did not account for in the neural network. Just to summarize the advantages and limitations of this method. The advantage is that you basically don't need to understand the MR physics of your host sequence in order to do quantitative mapping. And this might be ideally result in more accurate values, especially for sequences which are rather complicated. Obviously, this has limitations. We are we require a gold standard data set, and we depend on our test data set. For example, if you would change the delta TE or other sequence parameters in our sequence, the model would not fit anymore. And there's still an analytical model within the gold standard value, and the gold standard might not be true anymore. So in the future, we want to take into account the spatial information, so we maybe go towards a convolutional neural network. We also want to explore the variations due to sequence parameters, so maybe we can use just sequence parameters in our linear regression as a predictor. And the questions are, do we still have the same, is the model still okay in pathology? And can we maybe apply the exact same method to different approaches, for example, doing T1 mapping using an SPG sequence, or fingerprinting, or maybe even histology? Thank you.